Of the 7 remaining planets in the solar system, Mars is the most anticipated for the possibility of extraterrestrial life. After years of studying Mars' atmosphere, scientists believe that about 3.5 billion years ago, the planet had an atmosphere thick enough for water to flow on its surface. Current images of the Martian surface show the existence of vast plains located away from ocean boundaries. Meanwhile, the surface also shows some evidence that rocks were once submerged in water in the past. However, for some reason, it caused Mars' atmosphere to gradually thin out. To this day, scientists still cannot explain the cause of this phenomenon. The Martian atmosphere is a layer of mixed gases and small suspended solid and liquid dust particles surrounding the planet, held in place by Mars' gravitational force. From early observations to the present, Mars has always appeared as a world both alien and familiar. The first person to provide scientific evidence of the presence of an atmosphere on Mars was astronomer William Herschel. In 1783, through a telescope, he observed signs of clouds and haze on the planet's surface. 4 years later, John Hanks Ruster also drew similar conclusions through his observations. However, by 1830, Beer and Madler, after constructing a better telescope, made decisive observations. The hypothesis of fish shoals in Martian clouds is entirely baseless. However, the idea that Mars' atmosphere once contained abundant water vapor still receives widespread support. In 1870, Richard Proctor even hypothesized that oceans and life existed on Mars. The hypothesis of canals and water vapor on Mars sparked a lively debate in the early 20th century. In 1909, Campbell confirmed that he found no signs of water vapor. This completely contradicted the earlier claims of astronomers Vesto Slipher and Frank Very. In the early 20th century, scientists gradually realized that Mars has a very dry atmosphere and extremely low atmospheric pressure. Surface pressure at about 87 millibars, equivalent to 0.087 times Earth. Consistent with Vauquelin's earlier observations, this result reaffirmed the accuracy of his research. However, it was not until the space exploration era that Mars' atmosphere was studied in detail. The first close-up image showed impact craters left by meteorites on the surface, looking exactly like a desert. In 1965, the Mariner 4 probe sent these images back to Earth. Mars appears as the largest desert in the solar system, with an atmosphere characterized by suspended pink oxide dust clouds. Subsequently, signals from the Mariner 9 spacecraft spectrometer and camera showed the existence of very thick dust layers, and confirmed the existence of water ice clouds and dry ice, frozen CO, clouds on Mars. From 1976 to 1982, the 2 Viking 1 and Viking 2 landers sent a massive amount of data back to Earth. The passage shows many details of an atmospheric structure including both the troposphere and stratosphere, consisting mainly of methane, with thin layers containing water ice and rock at the boundaries between these layers. In the past 10 years, a series of explorations with unprecedented international cooperation have aimed beyond even Mars. Currently, data about Mars and its atmosphere is being transmitted to Earth at an extremely rapid pace, including some discoveries, among them fairly clear evidence of the past existence of liquid water. Similar to Mars' current underground water reservoirs, the presence of methane in local climatic regions. The Martian atmosphere is composed mainly of 95.32% carbon dioxide, unsuitable for human life. Many scientists believe that in the past, Mars had a much denser atmosphere, and water once flowed in rivers, emptying into oceans on the planet. Today, only a very small amount of water vapor is observed in Mars' lower atmosphere. Occasionally, they condense into ice cloud bands, or in rare cases, form thunderclouds containing hail. The atmosphere on Mars is very thin, so the wind always blows quite strongly, enough to lift the very fine dust layer on the planet's surface. In summer, wind speeds typically range gently around 2 to 7 meters per second, while in autumn, winds blow stronger with average speeds of about 5 to 10 meters per second. And stronger at about 17 to 30 meters per second on land during dust storm seasons. Blown up from the ground by wind, dust particles continuously float in the Martian atmosphere. They are yellow or red due to containing abundant carotenoid pigments. They create the characteristic fiery red sky of Mars during the day. They are the main component helping to warm Mars' climate, reducing the temperature difference between day and night. Occasionally, strong whirlwinds trigger dust storms, covering the entire red planet. This sudden occurrence completely changed Mars' climate within just a few weeks, then quickly disappeared. Dust from wildfires can also cause this phenomenon at sunset and dawn. The sky on Mars will appear blue. This is due to the scattering function of Martian dust radiating uniformly in all directions. Red light has a longer wavelength so scatters less, while blue light has a shorter wavelength so is mainly concentrated forward. When the sun is near the horizon, light must pass through a thicker atmospheric layer to shine directly onto the ground. Because red light is scattered in other directions while traveling, only blue light shines directly onto the ground. As the sun gradually sets below the horizon, the appearance of high-altitude clouds can refract light, casting a blue hue onto the ground. Clouds on Mars are formed from water vapor, and when carbon dioxide frequently condenses, it forms tiny ice particles that float suspended. They create white cloud bands, sometimes tinged with gold due to mixed dust particles. Equatorial low-pressure troughs are typically located at an altitude of about 16 kilometers. The mesosphere lies at an altitude of 40 to 100 kilometers above the ground. The condensation of water vapor into clouds indicates that atmospheric water vapor around volcanic areas has reached saturation, and may be an important sign in studying the transformation of water vapor and meteorological phenomena in the Martian atmosphere. The vertical structure of the Martian atmospheric layers, including changes in pressure and temperature, is very complex. The balance between convective flow and heat transfer will determine this phenomenon. The atmosphere absorbs energy from the sun and loses heat to space through radiation. Basically, the dynamic processes in the Martian atmosphere are very similar to those in Earth's atmosphere. The reason is that all these physical principles originate from the same hydrodynamic equations. Large-scale meteorological prediction models on Mars, such as GFDL, LMD, or OOPP, are divided into two main parts. The dynamical computation part represents global-scale interactions, while the radiative transfer part represents regional meteorological transformations. Under the influence of solar energy as a heat source, these models fully utilize the dynamical computation methods from meteorological prediction models used on Earth. The only difference between meteorological prediction on Earth and on Mars lies in the atmospheric radiative transfer process, where dust and clouds on Mars play an extremely important role. Examples of similarities between Martian and Earth atmospheric dynamics can be illustrated by the existence of the Hadley circulation, creating strange winds, heat waves, and vortices. Earth's movement around the Sun creates the cycle of day and night and the annual cycle of seasons. The presence of dust in local radiative transfer has created very characteristic dynamic phenomena. Notably, the phenomenon of dust being blown from the ground into the atmosphere. This is a highly random phenomenon and is not yet thoroughly understood by science. Although this phenomenon occurs only on a local scale, the dust lifting force is proportional to the wind stress at the surface. It is still common to see dust being lifted from the ground simultaneously on a global scale, creating seasonal dust storms. No physical mechanism has yet been established to explain the connection between global-scale dust storms and local-scale dust events. This is one of the sources of high costs for efforts to maintain meteorological stations on Mars. Based on existing research results, the evolution of the Martian atmosphere since the planet formed with the solar system can be summarized as follows. When first formed, Mars' atmosphere was probably similar to that of Venus and Earth at that time. Meaning these atmospheres had pressures around 10 to the power of 6 to 10 to the power of 7 pascals, primarily composed of carbon dioxide and some nitrogen. In the next stage, as on Earth, most carbon dioxide reacted with surface minerals and was absorbed into them, causing atmospheric pressure to gradually decrease. Unlike Earth and Venus, due to its smaller mass, Mars has weaker gravity, leading to a lower escape velocity. Ultraviolet radiation from the Sun breaks down gas molecules in the upper atmosphere into lighter atoms. Through thermal collisions, they achieve velocities greater than Mars' escape velocity. Weak gravitational pull, causing the planet Mars' small mass cannot retain thermal energy as long as Earth or Venus. Volcanic activities released large amounts of methane into the atmosphere, but this source was quickly depleted due to rapid consumption and the planet's internal heat. Due to no new supply and loss through the described processes, Mars' atmosphere became as thin as it is today. One of the most important questions still under exploration is, where did the water on Mars go? Erosion traces on the surface caused by water, along with dry ancient riverbeds and streams that flowed into seas, remain to this day. Evidence shows that water and water vapor once existed on Mars. So why have they disappeared today? Many hypotheses have been proposed, the most prominent being the irreversible greenhouse effect hypothesis and the asteroid impact hypothesis. The first hypothesis suggests that in the distant past, solar radiation heated Mars' atmosphere to a point where atmospheric water vapor increased significantly. Water vapor rose to high altitudes, where ultraviolet rays decomposed it into hydrogen and oxygen gas. These atoms, especially hydrogen, escaped Mars' weak gravity. Oxygen atoms not fast enough to escape the atmosphere were also lost through surface oxidation, forming a thin layer of oxygen dust. The second hypothesis suggests that a massive asteroid impact permanently altered Mars' atmosphere. Some traces on the planet's surface can be seen as evidence of a violent impact having occurred. Exploration programs have been proposed to test this hypothesis by landing on Mars' two natural satellites, Phobos and Deimos. To find debris ejected from the impact, which is trapped on these two satellites.